everyone, and thank you for joining my talk about how and why we use RayServe for implementing our fully automated digital authentication service called Validator. My name is Tanja Bayer, and I graduated from Karlsruhe Institute of Technology in 2018. Afterwards, I started working as a machine learning engineer, and right now I'm working for Widas Technologie Services in Germany, and my focus is on developing and deploying computer vision and machine learning services for our product called CDAS. Before I start right into my topic, let's have a quick look on what you can expect from this talk. First, I'd like to talk about what a fully automated digital authentication service is, and then I will go into detail why we use Ray and RayServe for implementing it. Afterwards, I will tell you how we moved from our first proof of concept to our current scalable and stable architecture. And afterwards, I will go and address some challenges we were facing and how we solved them by using Ray-specific implementations. So let's start. What's a fully automated digital authentication service? This is a service which you require when you, for example, want to sign an online contract and you need to identify it. So, for example, if you want to create a bank account, you need to identify yourself with a valid identity card. Right now, something like that happens by making a call with a customer service member where you need to enable your camera and you need to present your identity card to this person, and the person validates your identity card. Our system is differently, however, because it doesn't require another person on the other end of the video recording. Everything is done automatically and processed by machine learning and computer vision algorithms. So how does the process look like? When you want to register for your online bank account, you get redirected to our system, and the system asks you to show the front side of your identity card to the camera. You need to tilt your identity card so that optical variable security features become visible. Afterwards, you're asked to rotate the card and show the backside of the ID card. And in the last step, you need to interact with the system while your face is being recorded to make sure that really a human being and a live human being is interacting with the system. So what happens during this process? The data we are getting is visual data from the front side, video data from the back side, and video of the face of the person. This data needs to be processed and several things need to be taken into consideration. So for example, we need to check if the person who is interacting with the system is actually a live person. We need to make sure that the data on the identity document matches the data the person registered with. We need to make sure that the identity document is actually a valid document. And we also need to ensure that the person is matching from a biometric perspective, the person on the identity document. And last but not least, we also need to make sure that the identity card which is being used is a valid document and is not manipulated and contains all optical security features. All of those checks need to be performed and integrated into one final output. If the validation then is correctly, the customer is able to continue making his online account. So let's have a look on how we did get started. Our first proof of concept was not about having a scalable architecture, but about proving that we are able to develop models and algorithms for verifying and extracting the data. So we started with a two-splitted backend, where one part was using a state machine approach, a simple state machine approach, which was going through several steps for checking the validity of the data presented. And the other part was a web server which accepted the user requests from the web app and sent them via asynchronous communication to our worker backend. This asynchronous communication was done via Kafka Streams, and the data was shared via Redis. So once we had a first working proof of concept, we needed to make sure we're able to scale up the architecture. For that, we split up our whole process in small tasks and came up with a graph similar to the one you see on the slide. Splitting up all of that resulted in different requirements for different tasks. So like you can see, there were some tasks which can be performed in parallel. Others required the input from one or even more other tasks to start processing. Some of the tasks were really fast in computation and others were a bit more time consuming. Additionally, we also needed to run some of the tasks on GPUs because we have machine learning models which should run in at least near real time. Looking at the graph, one important thing also here is that we are not getting the data at once, but we get it in 3 different steps. So first, we get the data for the front side of the card. Afterwards, after some delay, we get the back side of the data, and then we get the face data. But in the end, we still need to make sure that this data is considered into one final output. So we need to make sure that all the tasks are synchronized with each other. After we came up with this architecture, with this graph, the question was, what are the correct frameworks to use for deploying this graph? And we had a look on several different frameworks, but we made a first selection based on the performance in distributed and parallel processing, as well as scalability. And the 4 frameworks which we came up with were Ray, which we didn't use so far, but we already read about it. Kafka, which we already had in place in some of the projects before. PySpark, which we also didn't use so far. And the classical microservice architecture, where we already have some experience with, and where we have a lot of different frameworks which can be used in Python, for example, IOHTTP or FastAPI. So after having a look on those frameworks, we needed to consider them for some more requirements. One of the requirements was the support of Python as a programming language, because it is the most common language right now for machine learning and data scientists, and hence enables us to fast progress in developing in this language. And additionally, we also needed to make sure we were able to transport our already implemented model into the framework without any additional effort. Like I already said, we also required to handle video data. If you store them in NumPy arrays, they become quite large in the memory. And when sending them in between the different tasks, we need to make sure we don't lose any performance here. So this was also something we definitely needed to consider when selecting a framework. And additionally, we also had a look into the community behind the frameworks and the adoption of the frameworks, because that makes sense in our opinion, because if the community is big and the adoption is big, you have a lot of possibilities to exchange with other developers how they solve problems, and you're faster in adapting the framework yourself. Considering all of those things, we made a decision to continue with Ray because in our opinion, it was the best solution addressing all those requirements. So then we started implementing a first skeleton of our process in Ray Serve. And we had also some discussions with members of the Ray development team. And we quickly came to a decision, instead of using plain Ray core, to use Ray Serve for implementing our architecture. There were several reasons for that. One of the reasons was that we could use one framework for everything. With using Ray core, we would have needed an additional HTTP server, and Ray Serve already provides the HTTP server for us. Another benefit with Ray Serve is also the native support of composing machine learning models, and the possibility to design a graph like the one we saw before by passing Ray Serve handles into other models. And finally, the possibility of shadow testing and the easy possibility of doing shadow testing with Ray Serve is also a benefit, because it enables us to test models before really deploying them into production and getting the results from them. So after we decided to switch to Ray Serve, and we came up with this idea of how we can implement our architecture, we had a closer look on how we can design our cluster. And we came up with the idea to split up our cluster into 3 different smaller clusters. One was the CPU cluster, another was a GPU cluster, and the last one was a REST API cluster. All of those clusters can be scaled up independently or together based on the process requirements we have. And all of those clusters were running on our on-prem cluster, and the deployment was handled by some of our other architecture services. Let's have a closer look on the different parts of our cluster. The CPU cluster runs mainly computer vision algorithms and also does some pre-processing for our for the data which we require for our machine learning models. One thing when implementing algorithms for our CPU cluster was the multi-core processing possibility of some of the frameworks which we use. So for example, NumPy, TensorFlow. And by default, all of them are able to do multi-processing, which normally is really good because it speeds up your algorithms, and they are able to run faster because they can use more cores than only one. But when running the algorithms in Ray, this makes the CPU cluster consumption a bit unpredictable, and that's why we didn't want to have it in our cluster. The good thing with Ray is also that it disables this behavior for most of the libraries already. So it sets the variable OMP num threads to 1, which means it disables the multi-core processing functionality for NumPy or TensorFlow. However, we found that still quite some of our algorithms were not sticking to the 1 core requirement, which we set for the backend. They still used more than this 1 core. And after some research, we found out that OpenCV doesn't consider the OMP num thread variable, but it has its own way of implementing and disabling this multi-processing functionality. So you just need to call the function setNumThreads variable and input 0, and then the multi-threading is also disabled for OpenCV. Another thing which we came across when implementing our CPU cluster was the static nature of the Ray Serve backends. When designing the graph, you always need to provide the number of CPU cores which are required for each backend. When the backend is then scaled up, it already reserves those requirements although they are not being used unless the backend is really executing the task which is meant for. If you remember the graph that we had before, not all of the processes really run in parallel. Many of them also run in sequence. And thereby this static nature would mean that we would need to block more resources than the ones which would be actually used by one process. And that would mean we would need to have more CPUs in our cluster than really required. So for overcoming this issue, there were two possibilities. One was either to assign less resources per backend. So pretending one backend uses, for example, only 50% of its resources, while it uses one complete core. And the other one was starting the whole Ray cluster by pretending we have more nodes than actually available. We decided to go with the latter approach because that enables us to always know how many resources are actually required by a backend, and that's better for scaling up further backends when required. So when starting our Ray cluster, we just passed in the num CPU variable, and we added the original number, of course, and added some more to overcome the issue with the too many resources. Additionally, for the CPU cluster, we also provided custom resources because those custom resources helped us to make sure that each backend which should come up on a CPU cluster is really assigned to the CPU cluster and not to some other cluster which also has CPU cores available. The GPU cluster is mainly there for running machine learning models, and all of those machine learning backends always only run one task in sequence, so they're not doing asynchronous processing of the input values. They're doing one task after each other. This behavior is really good in this case because we always know how many CPU cores are actually being used. And by that, we can make sure that not all 100% of the CPU's cores are used. And that's also the reason why we decided to put our Ray head node on this cluster, because in that way, we can ensure it doesn't lose performance because of too many CPU cores being occupied by other tasks. And we also decided to starting our Ray serve backends from here, just out of convenience, because that way we don't need to check if a head cluster is up and running before serving our backends. And the head node was started with the normal startup commands and passing in the number of GPUs we have there. The last cluster, the API cluster, has the main focus on high availability, because we always need to make sure that when a user request is incoming, it is handled instantly. So even if we have some processes being queued up for processing in our CPU cluster, the API cluster is always able to instantly communicate back to the user. Also on this API clusters, we have some data actors, which I will go into detail in the next slide. They're actually there for synchronizing tasks between all the clusters and for sharing some data. They also need to be highly available, and that's why we also put them on this cluster. And this cluster, similar to the CPU cluster, also gets started with custom resources, because we also want to make sure that all API backends are only spawned on this cluster, and all actors are also only spawned on this cluster. So now that we have the overall architecture, the only question which was missing was how are we able to synchronize the tasks, so that one task only starts executing when the data of the task before is there. And especially the main problem here was how are we able to make sure the data which is required, so the data either from front, back, or face is already there when the task starts. We decided to go here with the array actor approach and with asynchronous events. Our array actor is only there for communicating and triggering events, and also slightly for syncing data in between different tasks. So it is not really CPU heavy, and that's why we assigned 0.1 number of resources to it. When initializing the case actor, we need to make sure that we're making the asynchronous events. We're providing asynchronous events. So we have one event for the face, one event from the front, and one event for the backside. To enable other processes now to await those events, we need to provide a function, which we called wait, and which needs to be asynchronous because it has the await in there. And depending on the input we get, it decides which event needs to be awaited. Once we have that one, the missing part is how are we able to trigger the events, how to start the events or to release the events when new data is incoming. And this is also by providing a function, which we call trigger, and which has a parameter for the different steps. And based on the steps, it sets the event and enables our functions to continue where they have been stopped by the await function. And the last function which our case actor has is an initialized function, which we use to make sure that the case actor has actually been initialized before using it. So for writing the main logic, let's imagine we have only two algorithms, two models which need to run. One of them takes the trigger of the face as an input, and the other one requires both the front part and the face trigger to start working. Both of those tasks can run in parallel as soon as all the data they require is available. And finally, we need to make sure to gather all the data together. For implementing this, we use a stateful backend, which gets handles for all of the models when initializing it. And later, when this backend is called, we first need to create a case actor, array actor, which we then can use to call the wait function and pass and store the object reference for this wait function in our trigger variables. Those trigger variables we then pass to the serve backends. And again, we just store the handles to those functions in a variable and don't await them. Because if we would await the model 1, in this case, with an await keyword, we will not be able to run the model 2 before model 1 is finished. And we don't want this because we want them to run as soon as all the data is available. So for finally getting all the output together, we in the end need to call the asynchronous wait function and need to make sure that all the functions have been finished before processing the data further. Now that we have the implementation of the actor and also of the main logic, what we're still requiring is how are we able to set up to start this process. Let's pretend we have one backend, which is called setup and which can be called directly from the user API, from the user web page. And when it is getting called, when a user starts his process, we need to create one actor instance with a unique ID. And we need to make sure that it has a detached lifetime, because if it doesn't have a detached lifetime, it would go out of scope and when the backend completes the process, and we would not be able to use it in other tasks. After creating the actor, which is actually done asynchronously in the backend, we need to make sure that the actor is really initialized, and that's why we call this initialize function, because it only returns after the actor has been created. And then we can start the main thread afterwards, because it requires our actor. It requires to access our actor. So the last thing which is now missing is triggering the events, because now we started our main thread and it's waiting for the data. So each time now we get the videos. So when we get the face video, for example, we also create an actor again, and we call the trigger function to start the process. So this enables us now to have one working graph, which is executed once all data is there, and the final output in the end can be gathered together. So now let me have a quick sum up of everything. By using RayServe instead of our initial proof of concept, we were able to speed up the processing time about factor 4 compared to how we initially implemented it. Using RayServe also helped us to reduce the number of used frameworks, which also has the side effect that it reduces maintenance effort for maintaining all those different frameworks. And additionally, RayServe also provided us the easy scalability possibilities for our service, and it also provides us the possibilities to deploy different services with different configurations. And for the future, we are really excited to see how new features are implemented in Ray and RayServe. And one thing which we're especially eager to see is the load-based auto-scaling feature, which is right now already in the backlog of Ray, and we hope it will be implemented soon, because that also would help us solve some of the scaling problems we have at the moment, which needs to be done right now manually. So now I'm at the end, and I'd like to thank you for listening, and also a special thank to AnyScale and the whole Ray team for hosting this summit.